In this video, we are going to be introducing the multiplication and division properties and how they come about in proofs. To help you think through these properties, we're going to start with an introduction, looking at some other ways we can think about trisection points, midpoints, and angle bisectors. So here's what we have given below. In this figure, we are told that point B, C, F, and G are trisection points. So I want you to think about the definition of what it means to have trisection points. It means that those points divide the segment into congruent segments, three congruent segments. So as I've shown here, I have marked that AB, BC, and CD are all congruent to each other. On the other segment, points F and G also divide the segment into three congruent segments. So I have marked that they are congruent to each other. Notice I am using different tick marks because we don't know anything about the relative lengths of the two different segments to each other. Okay, but now we're going to think about this a bit more algebraically. So we know not only are AB, BC, and CD congruent, but that means that AB is 1/3, one out of three pieces of this segment exactly. And so if I were to ask what would the length 3 times the length of segment AB equal, it would equal the length of segment AD, which is the full length of this segment, because AB's length is equivalent to the other two parts. Multiplying its length by 3 would equal the length of the full segment. On the other side, that also will work for segment FG. 3 times segment FG, that is one of the three congruent pieces of segment EH, will equal the length of the full segment. That is multiplying one part to equal the length of the whole thing, since we know it has been divided into three equal parts. This wouldn't work if we didn't know we had trisection points. On the other side, we can reverse this. Let's say I'm curious about the length of the full segment AD. If I were to take 1/3 of the full segment or divide it by 3, the number that I result in would equal the length of segment AB, BC, or CD. I chose to list all three, and we could have picked one, and the same holds for EH. So now, not only do we have our regular definition of trisection points, it makes congruent segments, we're adding a multiplication and division relationship to them. So now, as I've said, there's no relationship between the two segments. So now let's add some in. Let's say that I pick a number. Let's say that EF and AB were both equal to 3. So both of these segments had a length of 3. The question is, what can we say about the measures of AD and of EH? Well, two ways to think about this. One, we know all three parts are going to be 3. We could add them up, and that will make them both equal 9. But more connected to our current section, let's think about a multiplication relationship. I know up here that AD is 3 times AB, so that still gives 9. And 3 times FG gives EH. Because I'm multiplying segments of the same value by 3, they end up equaling 9, and that would make them congruent because they have the same measure. Does this work if we generalize this, if we take away the number? It sure does. So if I just were to say that AB and EF were congruent to each other, so I'm going to add a little congruent mark here. Here's what we know. I know that AB and EF are congruent to each other, so that means that they have to have the same length. I also know that each of those are one part out of three parts of the whole segment, and so that would mean that the rest of the whole segment multiplied by 3 would AD, and the other segment EH would have to be congruent to each other. They're going to have to be the same size. Using the example of 3, we can see how they both came out to be 9, but we could have chosen any number, and AD and EH will always be congruent. Okay, there is another example here, but I'm going to skip that for the sake of time. That leads into the multiplication property. The multiplication property says this: if two angles, this also works as well, so I'm going to add this in here, or segments are congruent, then their like multiples are congruent. So the multiples would be if I were to able to double because I had some midpoints or triple because of trisection points, the resulting longer segments are going to be congruent. On the other side, this works if we are taking congruent angles and we are dividing them. So let's look above. We have two angles, and they both have angle bisectors. So that means we know that in the two angles, their angles are congruent. If I were to say that both angle JKM and angle NPR had a measure of 50, we want to ask ourselves, what could we conclude about angle JKO and NPS? Well, JKO is half of JKM, which makes it 50 degrees. NPS is half of NPR, which makes it 25 degrees. I said the wrong number. And that makes them both come out to be 25 degrees, which means that they are congruent. The question is, would that have worked if I used a number other than 50? Absolutely. Each time the two angles that we are trying to prove congruent are half of angles that we're saying are congruent to each other. That's the division property. The division property says this: if two angles or segments are congruent to each other, then their like divisions are also congruent. These properties are probably going to be the hardest ones for us to wrap our brains around, so we're going to look at some simple examples and then some more challenging proofs. Before we do that, here are some tips. When it comes to using the multiplication and the division property in proof, what you are going to look for is the double use 2 different times in different segments or angles of midpoints, trisectors, or bisectors in your given information or in your proof. This often means that we have 2 different angles or segments that are being divided into 2 equal halves or 3 equal parts, and we can use these effects of multiplication and division. Similar to addition and subtraction, we're going to use multiplication property when the segments or angles in our conclusion are greater than those in the given information, larger. Division property when the angles or segments in our conclusion are smaller. So let's look at very simply how multiplication and division properties would be used. So here is a set of 3 pieces of given information that allow us in one step to use multiplication property. Here's the first thing that we know. MO is congruent to NR. So I have 2 segments, and I know between those 2 segments, one of their pieces are congruent. I also know that O is the midpoint of MP. What does that mean about MO? It is half of MP. I also know that N is the midpoint of NS. What do I know about NR? It is half of NS. Okay, my goal here is to prove that MP is congruent to NS. Well, where are those segments? It's the full segment. So using the multiplication property says this: if I have 2 congruent segments, they are each half of some larger segment because they are both 2 segments divided by a midpoint. If I were to double these 2 congruent segments, it would result in the whole segments. Since I'm doubling 2 congruent measures, 2 equal measures, it means what we end up with will have to be congruent. A little bit hard to think through, so make sure you process this. So that allows us straight from the 3 givens to prove that MP is congruent to NS, our reason here being the multiplication property. As an important note, you do not need to state or prove what we usually do with midpoints, which would be something like MO is congruent to OP, the 2 pieces of MP, or NR is congruent to RS. You do not need to state that information by the definition of a midpoint to use multiplication property. We're using the midpoints slightly differently here, using them as half of the segment rather than 2 congruent segments. To show how division property shows up, here is a sample statement. So what we know first is angle TRY, which is this whole angle in the diagram on the left, is congruent to angle ABE, the whole diagram on the angle in the diagram on the right. We know that RW and RX trisect angle TRY. So this angle has been divided into 3 congruent angles. We could prove it, but we'll see here we don't need to. And BC, ray BC, and ray BD trisect angle ABE. So those 3 angles are congruent. Okay, the proof is asking us to prove that angle TRW is congruent to angle CBD. So where is that? TRW is here. CBD is here. Okay, remember the 2 angles are congruent. The congruent angles have each been divided equally into 3 congruent angles. What do we know about these two parts? Angle TRW is 1/3 of the whole angle. Angle CBD is 1/3 of the whole angle. Since they're congruent, dividing them both equally into thirds will yield congruent angles. So that makes for us here angle TRW congruent to angle CBD by the division property. All right, so what we're going to do is we're going to look at how this shows up in the context of a more involved proof. And we're going to look at the proof on the next page, example 3. Okay, so here's what we have. I'm actually going to remove my markings and mark it back here. Okay, there's a lot of information. As we get into larger proofs, with the abundance of information, it might start to feel overwhelming. So we want to take it slow and go piece by piece. First thing we have is that angle NOP is congruent to angle RPO. NOP, RPO. So make sure you find those angles and make sure that you mark them. Ray PT bisects angle RPO. So ray PT is here. RPO is the one we just marked as congruent. So you can, this is an optional marking, but just so I know this, I'm going to say, okay, these two angles, even though they don't look it, are congruent to each other. Okay, ray OS, that's here, bisects angle NOP. So that means these angles, different markings, because I don't know about their relationships, are congruent to each other. Okay, now there are some more givens. We know that angle NSO, where is that? That is right here. Right here. Angle NSO is complementary to angle 1. And angle RTP, right here, is complementary to angle 3. Whew, that's a lot of givens. All right, but before we go anywhere, what are we trying to prove? We are trying to prove the two angles I just put an arrow at, NSO and RTP. We're trying to prove that these angles are congruent to each other. Okay, it's a lot of information. Let's work backwards. So what do we know about NSO? And what do we know about RTP? Well, I know that NSO is complementary to angle 1, and I know that RTP is complementary to angle 3. So in this case, they're both complementary to 2 angles. This makes me start to think about our complements theorem. It says if we're complementary to, well, these aren't complementary to the same angle. And currently, I don't know anything about angle 1 and angle 3. But as a plan, if I could show angle 1 and 3 were congruent, NSO and RTP would be complementary to congruent angles. So now I've got a new goal. Is it possible, question mark, is it possible for me to prove angle 1 congruent to angle 3? Well, let's look at this. What do we know? Where is angle 1? Angle 1 is right here. Angle 3 is right here. They are both a part of the 2 bisected angles. The 2 bisected angles that are congruent. So this makes me think of division property. Division property says if I have 2 angles that are congruent, they are both bisected and both divided in half, their halves should be congruent. And so we can prove angle 1 congruent to angle 3 by the division property. We can do that here. So now that we've proved angle 1 congruent to angle 3 using the division property, the large angles, so we needed all 3 pieces here. The angles are congruent. The bisector told us that each angle is divided into 2 congruent halves, and their halves would each be congruent to each other. Angle 1 congruent to angle 3. Now that we have done this, I know that the 2 angles I'm trying to prove congruent are complementary to congruent angles, so we can finish off our proof saying that angle NSO is congruent to angle RTP using our complements theorem. If angles are complementary to congruent angles, then they are congruent. We are going to stop here. We'll look at some more proofs tomorrow. If you are interested to look at another proof, we will work through this one tomorrow as well. So I'm actually going to remove. This is another proof that uses our different properties. We will look at this one more in depth tomorrow, but you're welcome to look at the key or take a look at this now and try to think through the steps and why they make sense to you.